So we speak about very, very interesting stuff about modular forms, something like that.
How do you know it's modular forms?
I'm guessing.
Thank you very much, Theron, for the invitation. I'm going to take the title of the seminar, the experimental math seminar, maybe one step too far, and make it an experiment in... the lecture will be an experiment. I haven't prepared anything. I thought we would have a casual discussion. I don't know what people, I'm expected to see graduate students and not all these...
As far as your topic is concerned, I am.
Right. So...
Okay, have a slide of you.
Okay. So, I thought I would just give a very basic introduction to the kinds of things people who today call themselves number theorists think about, and try to convince you that at some point in time, at least, what they were thinking about was number theory. So, so where should we start? I guess we have to define number theory, which is an impossible task, right? But certainly, if you think about prime numbers, then you count as a number theorist. I mean, if you think about integers, if you're a discrete mathematician, are you a number theorist, or are you a combinatorialist, or are you a discrete mathematician, or a statistician, or whatever? So these words are all loaded, right? So what's a number theorist?
No, number theorists are interested in numbers for their own sake.
Okay. Well, all mathematicians, I mean, that's interesting mathematicians and physicists, right? We're interested in theorems for their own sake, not because of anything. So if the thing you think about are numbers, okay, you're a number theorist if you're a mathematician.
No, when I count something, I like to have the answer to the number, but don't care if it's prime or not.
Okay, so number theorists don't necessarily care. I mean, it's true that primes. Okay, so is primes the thing that distinguishes a number theorist from just a discrete mathematician?
No, properties of numbers.
Properties of numbers, exactly. Okay. Well, okay, so there are all kinds of things that you can study. You can study, right, the number of partitions of a number, or what prime factors it has. These are all kinds of interesting things. So let's go back. Let's say number theorists study primes. Let's be very crude. So this is why I don't like going to cameras much, because then I can't say outlandish things that I'll later want to take back. So number theorists, number theory equals primes. So let's be very, very wrong. So we care about primes. What about primes? Well, we know there's infinitely many from Euclid. What's their distribution? So the distribution of primes how many pi of x is how many primes are there, number of primes of x. And this was kind of the first hint that people studying primes are going to end up studying other things to learn things about primes. I'm telling serious people about the Riemann zeta function. Right? Okay, so grad students, I'm talking to you, even though you're all hiding in the back because there's grown-ups here. How would you access this thing? You would think there should be some just purely combinatorial, right? You use sieve or something. You do something very crude, and you get your hands on it. In fact, there is a crude way to get your hands on. So the prime number theorem says that pi of x is asymptotic to a graduate student. Please tell me the answer. It's good that the number theory graduate students right here.
It's about x over natural log of x.
Okay, so I'll put x over log x here. I'll put it there. So log is always natural log. There's no other base for me. All the others are unnatural. So this statement isn't wrong, but it's wrong.
Be Li of x.
It should be Li of x. It should be the correct answer. So let me put it there. But let's say better is that pi of x is equal to, asymptotic, but Li of x by definition is the integral from, doesn't matter where you start, 2 to x dt over log t. Okay, logarithmic integral function. And why is this better? Well, I claim that pi of x is equal to x over log x plus big omega of x over log squared x. In other words, if you approximate pi of x by x over log x, that difference will fluctuate as large as a constant times x over log squared x infinitely often. As opposed to what we actually know about the prime number theorem. So the prime number theorem, this is still a weak form. We know better forms, but what we know is that it's lie of x plus big O of, let's say, x over log to the million x.
No, we know much more.
We know much more.
Yeah, what we can prove.
Very good point. Very good point. We know much more. Okay, so we know the Riemann hypothesis. We just can't prove it. Pi of x is lie of x plus big O. It's x to the half plus epsilon. Maybe there's a log. Again, the camera's rolling, so let me put log squared. It's x to the half plus epsilon. Okay, so this is what we know. This is weaker than what we can prove. We can prove stronger than that, but not by much. Anyway, so why is this the wrong answer? Because exercise. The exercise is for the grown-ups, not for the students. Lie of x is equal to x over log x plus x over log squared x plus x over log cubed x. You should stop in finite time because that series isn't going to converge, plus big O of x over log to the 4x. Okay? So if you're just taking this as your estimate, then there is a lower order term that's going to that will be there. So this is exercise. All right, so that's what we can prove, not what we know. How do you prove this? So why is that the Riemann hypothesis? How do you prove it? I'm again asking the graduate students.
Wait, how do you prove the Riemann hypothesis?
Yes, please tell me, because I'll be very happy to take what you say and write it down and put my name on it.
Ask me next week.
Yeah. How do we prove the prime number theorem?
I know how you prove them, but you kidnap Alice Kontorovich and told him that he proved it. Yes, and nothing else.
So I'm teaching complex analysis in the fall, graduate complex analysis, so we'll prove the prime number theorem. You don't have to kidnap yet, you just wait.
No, then you probably do work on other problems that are easy that you can publish.
Okay.
Because you're worried about your promotion. Or by publishing and practicing. If you focus full time on your publishing,
Well, I mean, I've heard stories of a whole bunch of, in 1905, like 1900 and 1905, there were so many brilliant people who left mathematics because they were not able to obtain their PhD. Because the prime number theorem, so the Riemann hypothesis is stated in 1859, and the prime number theorem is proved in 1896 by Hadamard and Delvalle-Poussin. And okay, we know how to prove the prime number theorem. We just need to go a little bit farther and we get the Riemann hypothesis. So there was a large period where anyone was assigned the Riemann hypothesis, and they couldn't solve their thesis, they couldn't graduate.
I know how to prove it in the Russian way. Okay, somebody say, why don't you stupid? Why cannot you prove it?
Yeah. It works for some things. Somehow it hasn't worked for the Riemann hypothesis. Okay, so graduate students, what's the correct object? Again, for various reasons, the correct object to study. The Riemann.
Zeta function.
Cheating. You're not. Okay, you want to be a graduate student now? Right. So it's the zeta function, right? So what's the Riemann zeta function? It seems at first like it has nothing to do with primes because it's a function about integers. sum n goes from 1 to infinity, 1 over n to the s, right? And this converges if the real part of s is greater than 1. And it has a functional equation. In the, there's the standard form, I to the minus s over 2 gamma of s over 2 zeta of s. This is some standard function. There's a good reason for this to use this function, but actually there's a good reason not to use this function. Maybe I'll say something about that. And this is exactly the same as this xi function at 1 minus s. And this functional equation actually was proved by Euler. Most people think it's Riemann. It was proved by Euler in a fascinating paper. So Euler knows how to compute, so everybody knows what zeta of 2 is, right? This is how Euler got famous. He proved zeta of 2, pi squared over 6. All right. And then once he computed zeta of 2, he computed zeta of 4, and then zeta of 6, and zeta of all of the, he learned from the Bernoulli brothers, so in terms of the Bernoulli numbers and the very regular powers of pi, he was able to express all of the zetas. Zeta of 3, does anybody know what zeta of 3 is in terms of pi's and e's and other constants that we know? That would be another good problem. For that one, I think you should grab the Ron and capture him and hold him locked up so he thinks about nothing but zeta of 3. And then Euler
It's not
computed...
expressible in terms of pi and e. You know?
Can you prove that?
No, I know it.
You know it, yes, of course. There's an oracle that tells you things are true. Is that a proof? So Euler then computes zeta of minus 1. So what in the world does zeta of minus 1 mean? Zeta of minus 1 means 1 plus n plus 1 plus 2 plus 3 plus 4 plus 5 and so on. He computes this. Now, he says, I can't quite make sense of what this calculation is. It's kind of a fascinating, there's not a projector here, is there? There is, but I'd have to find this paper, but, okay. Ask me afterwards if you want me to find this paper, because you can really just see, he writes this series, and he says, I don't understand, but I get a number at the end, and the number is something very reasonable, and then he does it for zeta of minus 3, and then he does it for zeta of minus 5. And he realizes that there's a relationship between these numbers and these numbers, and then he states this theorem in his language, which will be factorials instead of the gamma function. The powers of pi line up, zetas line up, and he says, I think this happens all the time, but I can't quite prove it. So all the time for him would not be complex valued. He didn't understand the right way to interpret this. Of course, we call this the Riemann zeta function and the Riemann functional equation, but Euler knew the function. Okay, why do you care about this thing? What is it about this thing that, how does it connect to the primes?
You can rewrite it as a product.
Yes, the Euler product formula. So Euler, the same Euler. So I'm teaching cryptography now. What's that movie about? What's it called? With that guy playing.
The Imitation.
The Imitation Game. Thank you. And the guy's name is
Benedict Cumberbatch.
Benedict Cumberbatch, right? And the girl's name is Keira Knightley. So my students told me, oh, you have to go see this movie. But Keira Knightley says Euler. And you would think these guys have so much money, they get so much. Anyway, Euler. So the Euler product formula. The Euler product formula, I'll let you verify. You probably know it already. If you don't know it, convince yourself that this formula is correct. That's the relationship between this continuous thing and this discrete thing, is that the discrete thing sees the products of primes. Now that's still, how in the world are you still supposed to use that thing and compare it to the number of primes up to x? So the right prime number theorem is actually is actually much nicer than this prime number theorem. There's this weird function lie of x in there. It's kind of not so natural. The right prime number theorem is the following. If you sum the primes up to x, but not 1, so that would be counting how many primes there are up to x. Instead of summing 1, you sum log x, log p. That's equal to x plus a small error. So again, we know the Riemann hypothesis. So okay, that's not the prime number. That's a much better statement. Right? And in fact, the even more correct statement is you don't just sum primes up to x, you sum prime powers up to x, weighted by log of the prime, which is that power, and this. So this is the correct formulation. It doesn't seem like the correct formulation because it seems like we did something much harder. This seems very natural. Right? How many primes are there up to x? Why is this the natural thing, the natural object? Well, if you're asking an analytic question, like estimate the number of primes up to x, it turns out that analytically this is the correct behaving function. Let me try to convince you of that. So let's take the log of zeta. So log of zeta, by this formula, it's a sum over the primes, instead of a product, of the logs of this. So this is minus log of 1 minus p to the minus s. And now I need to work out what minus log of 1 minus x is. Well, it's the integral of 1 over 1 minus x. 1 over 1 minus x is 1 plus x squared. So the integral will be x plus x squared over 2 plus x cubed over 3, and so on. So this is the same as sum over the primes. And now I sum k from 1 to infinity, and x to the k over k. So this is p to the minus sk over k. Is that close to the correct calculation? How does that help us? Doesn't help us too much yet. If we differentiate this with respect to s, so if I differentiate log, I get the logarithmic derivative, zeta prime over zeta. And on this side I get, so a sum over the primes, a sum over the integers, 1 over k. And now I have to differentiate p to the minus sk, p to the minus sk, which I'll write as e to the minus sk log p. I can't differentiate anything other than the exponential function. So if I differentiate that, I get the same p to the minus sk, but down comes a minus k log p. It's a derivative in s. Okay, so if I've done that right, the k's should cancel. The minus sign is a minus sign when you pull it all the way outside. And now I have a sum over all primes, over all positive integers, 1 over p to the sk. And there's a convenient way of packaging this together, which is to write it as a sum over all integers, 1 over n to the s. Thank you. 1 over n to the s, and then when does the integer n arise? It arises if it's a prime power. The only integers that arise are the integers that are primes or prime powers, and when they arise with this coefficient log p. This function has a name, it's the von Mangold. So lambda of n is the von Mangold function. It takes the value log p when n is some p power. N is 0 otherwise, and that's exactly what this is. So this is a sum n up to x of the von Mangold function. Because you're summing prime powers up to x weighted by log. Okay. Now, we did all these manipulations, but why have we actually learned something? The reason we've learned something is because Riemann knows complex analysis. So Riemann knows the Cauchy, he knows how to do a contour integral. So let me be crude. None of the integrals I'm about to write down converge absolutely, but never mind. Let's take an integral over some vertical line. So this means an integral over real part of s equals 2, from minus I infinity to plus I. And if I integrate x to the s, ds over s, let's evaluate this integral. Well, there are two cases. So x is some real number, right? If x is less than 1, so if x is less than 1, I have this contour. Of course, as I said, it doesn't converge absolutely. If I put absolute values, I just get x to the real part of s. Here and here I'd get 1 over, if I write s as sigma plus it, I only have 1 over t, which you can't integrate, so I leave it as an exercise to you to make this correct what I'm writing. But if x is less than 1, I'm going to pull the contour over to infinity this way. And pretend I can and make it, and you can, just you have to be more careful. Then what do I get? So let's say I pull the contour out to some capital A. Then then the integral, let's call this I of x. So I of x, in absolute value, is bounded by, well, again, pretend something converges, but this, okay, you see when you cheat too much, you get yourself in trouble. Basically, I have an x to a large power, and that x is less than 1, so I get something very small. Fuzzy. This has no meaning. This goes to 0, so if x, we get 0 if x is less than 1. Now what about if x is bigger than 1? Okay, so verify that the integral actually is 0 rigorously, and not this mafia jump. If x is bigger than 1, well, I just do the same thing, except I pull the contour that way, and I get 0 again. So this integral is everywhere 0.
Is there a singularity?
Yes, I've forgotten something. What have I forgotten? There's a pole. There's a pole at s equals 0. So when I do the pole this way, I pass that pole. And what's the residue of that pole? Well, it's just a simple pole with residue x to the s at s equals 0. So the residue is 1. So that's the indicator function of whether x is bigger than 1 or less than 1. Okay? When done properly, which I have here. Now comes Riemann's brilliant insight, which is, what happens if I take this zeta prime over zeta function and I multiply it by x to the s ds over s. And I integrate over some vertical line like 2, and there's some normalizing there. So look at this thing. Well, we know what zeta prime over s of s over s is. It's a sum, and of course, we can always, in number theory, whenever you get two sums or two integrals, you always get them in the wrong order. So just knee-jerk flip them. So we have a sum over the integers n. We have this integral, 1 over 2 pi I. We have a coefficient, which is this von Mangel function, lambda of n. 1 over 2 pi I, integral over a vertical line. What do I have? So this logarithmic derivative, I've pulled out the coefficient, and what's left is a 1 over n to the s. And then I've multiplied in an x to the s, ds over s. And what is this? This thing is just our function I, not at x, but at x over n. So this is either 0 if x over n is less than 1, or it's 1 if x over n is bigger than 1. Which is the same thing as n is less than x. So this is just a sum over all integers, except the only ones that play a role are the ones that are less than x. And those come with a weight 1 here, and a weight lambda here, there's our sum over the von Mangold function, arising as a complex contour integral involving the logarithmic derivative of the zeta function. Okay, Riemann makes this observation, and then he does exactly the same thing. He has some contour integral he's going to pull. Now all you have to know is where are the poles of zeta prime over zeta, and what are its residues. But where are the poles of the logarithmic derivative of a function as compared to the poles of the original function?
Poles and zeros of the original function.
The poles and the zeros. So the Riemann zeta function has a pole at s equals 1, if this is meant to be s equals 1. It has these trivial zeros here at the negative, but Euler knew this, by the way. He knew that zeta of negative 2 is 0. He computed that. So it has these so-called trivial zeros at the negative even integers. And then, on this line 1/2, Riemann knew that there's a whole bunch of zeros. In fact, infinitely many zeros of the Riemann zeta function are on this line 1/2, and then there could be some others. Well, we know that there aren't. Let me put them there just for fun. And if they're there, they come in conjugate pairs by the functional equation. Okay, so you pull this contour, you get a contribution at x equals 1, at s equals 1. And what is the residue at s equals 1? So somewhere I've lost my minus sign. There's a minus sign. That you guys were watching me carefully. There's a minus sign. And what's the contribution at s equals 1? I guess I don't like this minus sign, so let me put it here. So the poles of this function